Talking and talking and talking, we now proceed to the solution of 2a, where we wish to write down the distribution of k, where k is the number of observed ladder heights. Now, according to the definition in the exercise text, if the first ladder time is finite, then k is the number I, the greatest number I, such that the ith ladder time is observed. And if the first ladder time is infinite, then k is just 0, because then you have not observed any ladder heights. We want to find the distribution of k, and it's pretty clear that k is 0 or 1 or 2 or 3 or 4, etc., etc. So it follows a discrete distribution. What we first want to do is find the probability that k is equal to 0, for example. Let us try to consider that first. Well, note that k is equal to 0 if and only if the first ladder time is greater than infinity. Therefore, the probability that k is equal to 0 is equal to the probability that the first ladder time is greater than infinity. And the first ladder time is also just the same as the first inter ladder height time. And this is equal to 1 minus the probability that the first inter-ladder height time is finite, which is given by 1 minus the Rouen probability if the initial capital were 0. Recall from the lecture notes that the Rouen probability in the case that the initial capital is 0 is given by the arrival rate multiplied by the mean value of the claim size divided by the premium rate. And in our case, we have that the claim sizes are exponentially distributed with parameter theta, and therefore have mean value 1 divided by theta. Or at least that is how Hans Schmidli parameterizes. Well, that's the parameterization of Hans Schmidli anyways. So this is equal to 1 minus lambda divided by theta c. Now we've got this case out of the way, let us try to consider the other cases. So for some natural number n, what is then the probability that k is equal to n? Well, first of all, let us take a look at the event that k is equal to n. Then we can note that, well, when is k equal to n? Well, it is equal to n if and only if the first ladder time is finite, the second ladder time is finite, the third, and so on and so on, and the nth ladder time is finite, but the n plus first is not. So k is equal to n if and only if t1 is less than infinity and t2 minus less than infinity, and so on and so on, and the nth ladder time is less than infinity, whereas the n plus first ladder time is infinite, because then you observe all in all n ladder heights. How can we write this up in a different way? Well, we know that the first ladder time is finite if the first inter-ladder time is finite. And the second ladder time is finite if the first inter-ladder time is finite and the second inter-ladder time is finite. And so on and so on and so on. And the nth ladder time is finite if all of the first inter-ladder times until the nth inter-ladder time is finite, and the nth inter-ladder time is also finite. And the n plus first the n plus first ladder time is infinite if and only if the n plus first interladder time is infinite. The nice thing here is we have now written up the event that k is equal to n in terms of the intersection of multiple events, but where each of these events are in fact independent of each other, since the inter ladder height times are IID. And we also know the distribution of each of these. So we can now write the probability of k being equal to n. Well, that is just the probability of the first interladder time being finite and the second and the third up until the nth. So that's the probability of the intersection of the events that the ith ladder time is finite for I going from 1 to n. And that the n plus first ladder interladder time is infinite. And we may write that up as, well, thanks to independence, we may write that up as the product from 1 to n of the probability of the ith interladder time being finite, and then we multiply that by the probability of the n plus first interladder time being infinite. Now we know that the tau I are also identically distributed, and this therefore boils down to the product of this probability n times, and this probability was given over here. That is lambda multiplied by 1 over theta multiplied 1 over theta c. So we will have to take that to the nth, multiplied by this event here, which is just equal to multiplied by the probability of this event, which is just equal to 1 minus the probability of a finite n plus first interladder time, which is again just lambda divided by theta c. And this is the answer. Actually note that for n equal to 0, this formula also works, because then this first part is just equal to 1 and you get the probability of k being equal to 0. What we can also note is what we get is actually that k is negatively binomially distributed with parameter 1 comma lambda divided by theta c. It kind of depends on what your parametrization is for this to make sense. I think in Schmidtly they actually write 1 and 1 minus lambda over theta c. Basically, the negative binomial distribution describes the how can you say, the number of successes that you can get in a row before you stop the experiment due to a certain number of failures. And that certain number of failures is the first parameter, and we stop our experiment here as soon as we get one failure. And the second parameter is sometimes the failure probability in a string of independent experiments, and sometimes it's the success probability. So it really all depends on what your parametrization is. So we now know that the number of observed ladder heights, k, is negatively binomially distributed with this distribution here.